Yeah, so today I'm going to talk a little bit about how the mass spectrometer uh, works and a little bit more of details on the principles and some technical details also. So as we said last time, the basic mass spectrometer is three parts. One ion source to get molecules to get into the gas phase and acquire charge. Because in general, if a molecule doesn't have a charge, you don't see it in the mass spectrometer. It has to be ionized. Uh, so then we have the mass analyzer, and we're going to talk about a few different types of mass analyzers, and then the detector. And we'll mention a little bit about the detector, but not so much. And then, so the principle is that you have these three parts, and then in the end you get a mass spectrum, where you have mass divided by charge on the x-axis and intensity on the y-axis. And in general, I mean, the way it works is that if you have a lot of material, you will have a large intensity. But if you compare two different molecules, and one of them is, let's say, has a peak that's 10 times as intense as another one, you can't in general say that there is more of that material, because different molecules will have very different ionization, so that you will get large differences in even if in intensity, even if you have the same amount, if you have different chemical structures. So then we talked about a little bit a mass spectrometer with more parts, but it's pretty much repeating the same elements. So you still have an ion source. In this case, you have two mass analyzers and the fragmentation chamber in between, and then finally the detector. And the nice thing with this is that you can then run it in different modes. So first you survey what's there, and then you take one at a time and fragment them. And then here you see the peptide backbone, and the way we mostly do fragmentation is by colliding with a gas. So we get fragmentations at the peptide bond. And depending on if the charge is on the N terminus of the fragment side or on the Y terminus, we have different nomenclatures. So B is if the charge is on the N terminal side, so we get this piece. And then if the charge is on the C terminal side, we get a Y ion. And then we're going to talk, there are other types of fragmentation. One is called electron transfer dissociation, where you get instead C and Z ions. Those are and then at higher energies and for certain peptides, you can also get A ions in some cases. X ions, I think you only get when you have higher energies. So but the most common is the B and Y ions. Sorry? I mean, it is that's the weakest bond. When you have in the collision, when you have collisional energies, you have the energy has time to disperse throughout the molecule, and then it breaks at the bonds that are weakest. And that's why we also in collision in those dissociations have such large intensity differences depending on what's the amino acid on both sides. So for example, at prolines, we get a very large fragment peak usually. And things, but also the other amino acids, you see big difference. It's because the energy and the weakest bonds fall apart. And here it's the peptide bond where the two amino acids come together when the peptide is synthesized, and that's the one that breaks. And then we get these two. So the B ions, it has the N terminus of the peptide, and then at the fragment site, it has CO. And the Y ion it has the C-terminus of the peptide, which is the carboxylic group, and it has also an N-terminus that's the same as a peptide at the fragmentation site. And then it has a hydrogen, one proton that's attached to it. And that's not always defined exactly where it is. Depends on where there are basic residues.
So you would get equal probabilities of the B ions as well as the Y ions?
No. So that actually depends on the mass analyzer, and usually in most common mass analyzers, Y ions are more intense. Not always, it depends a little bit on the peptide also, but in general, in most spectra, one would see Y ions being more intense than B ions. And especially if you look in a time of light. So then, as we said before, we have complex mixtures, so we need to separate them. So we usually use liquid chromatography that can nicely be interfaced with especially one of the ionization methods that we're going to talk about. That's called electrospray. And then we usually we set up the instrument to switch between taking survey scan to see what's there at that time, to isolating one by one the peptides and fragmenting them, and then collecting a lot of spectra. So I mean, typically one would run maybe 2-3 hours, uh, run and collect up to even 50,000 spectra. So that's the sort of magnitude. So then ion sources. There are mainly two ion sources that people use nowadays. One is called matrix-assisted laser desorption ionization, and the other one is called electrospray ionization. So we'll start looking at electrospray. And here what we have the peptides in the liquid phase. So, and that's why it's so convenient to interface it with liquid chromatography, because after the column we connect the flow to a needle that's at high voltage. So see here, so the needle is at high voltage, and then the entrance to the mass spectrometer is at ground. And what happens then, and this tip of the needle is very thin, so what happens here that droplets are being formed. And one can look at it, and if one looks at it in microscope, it looks like a sneeze, but a more preferably a continuous sneeze if one does it, if it's done well. But sometimes it is the sneeze that it doesn't work very well. Anyway, so you get these thin droplets, and what we have usually is atmospheric pressure out here and vacuum in here. So what happens when these droplets go from atmospheric pressure to vacuum is that they start evaporating. And sometimes one can help the evaporation by having them go through a heated capillary. And then, so these droplets that contain peptides that are charged become smaller and smaller through evaporation. And at some point, the charge is too high to support the droplet, and then they fission. So they fall apart into smaller droplets. And then again, it continues the evaporation, and then they fission again, and so on. And then finally, we end up with just naked peptides that are charged, that go into the mass spectrometer. But again, one has to be careful to get as much of this spray into the mass spectrometer as possible, because it's a waste when, like in this picture, shows that a lot of it gets stuck on the wall here outside and doesn't make it in. So that's can be quite tricky to do that in an efficient way.
So how much, sorry for interrupting.
No, no, no.
Sample are you using at this step? Approximately like 10%, 20%,
I mean, it's more like you lose, I think more like 90% is typical.
90?
Yeah. I mean, it's more, yeah. I mean, people are trying to make it efficient, and maybe it's 50% sometimes, but it's a lot. It's difficult because you want to have a small hole, because you're pumping here, and you can't. I mean, you limited how much you can pump, and so that's. Yeah, so there's a lot of losses, I mean, especially companies are trying to optimize that all the time.
So hence you need a large sample to begin with.
Yes, yeah.
Could you recollect those loss samples?
One doesn't do that really. It's not. It's more a nuisance that you have to clean the instrument, because you have when these surfaces get covered with too much, and then it doesn't work as well. So you have to take it apart and clean it regularly. But yeah, but still the biggest problem is probably the sample preparation, where you have even more losses. So before that's really so. But I mean, it's definitely something that they're trying to optimize.
So how much starting material in terms of nanograms of protein would you need to get a fairly decent spectrum with this?
It varies a lot. And I don't have a good answer. It depends on how complex it is, how much detergents you have, how much other things you have. So it's a very difficult. You should ask that. So Beatrix Uberheide will come and give one of the lectures, and she runs the core facility here, and she will be able to give you a better answer. So then the other technique that was, so both these were, both electrospray and matrix laser absorption ionization was developed in the late 80s, about the same time they came out. So MALDI, here you have your sample on a solid surface. So what you do is you add a matrix, like a molecule like this, and people have tried a lot of different types of matrices. The main thing is, should be a molecule that when you dry it down, it should crystallize nicely, and it should be able to also um, incorporate the peptides and proteins into the crustal while it crystallizes, and it should absorb the laser light. So what will happen when you have this crystal with your peptides embedded in it? When you shine the laser on it, all the matrix molecules they absorb the light, and they explode, sort of, and then you get the peptides and the proteins get dragged out into the gas phase this way. And of course, as you can imagine, this is much more violent. If you want to look at non-covalent interactions, people usually try that in electrospray and not with MALDI. The other thing then you do is you have, again, your sample you usually put on a metal plate that's at high voltage, and then you have a grid at ground. And here now, this usually is also inside of vacuum. Usually, not always, but that's so here you don't have the problem that you have to go from atmospheric pressure to vacuum. So those were the two ion sources that we're going to talk about. So now we talk about a little bit about detectors. The two types that we're going to talk about. One is an electron multiplier. The other one is an image current. So electron multiplier is where you have your particle and it hits a surface that's made so that when your particle hits it, electrons will be ejected. And then you usually have some kind of geometry so that the electrons that get ejected then will continue colliding and multiplying. And at every collision, it will create more than one electron. So then in the end, you have a large current for every particle that comes in. And then the things that to consider when making these is that, first of all, you want them to recover fast so that you can measure many different things. So what people have done is to have many of these channels in a small area. So it's usually in some kind of glass plate that's coated in some way, so that you can have many small channels like this. So here you destroy your particle. I mean your molecule that you're measuring. Then for the image current, here what you do is you make your peptide go round and round inside a box where you have two electrodes, and you're measuring the image current. So what happens is that since this particle is charged, it will affect the electrons in the two electrodes, and you're going to get a signal from as this particle goes around many times. And that's what you then use to calculate its mass. And we're going to see later on, and you have to keep it usually in you use a magnetic field to make the particle go around. So then mass analyzers, there are quite a lot of different ones, and also people have combined them in different ways. Yeah.
What are the relative pros and cons between the two detectors? Is there one that you use for one specific kind of application versus?
Yes, so it's usually how you do the mass analyzer. So we're going to talk about the time of flight. There you use an electron multiplier, because you have the particles flying down, and then you and also the same with the magnetic sector, and usually with quadrupole is also. But for ion traps and Fourier transforms and orbit traps, there you use look at the mirror current. So that's so it depends. So it's very much related to the mass analyzer that you're using. So probably time of flight is the easiest one to understand. Oh, so before that, so what you always with any mass analyzer, you use a combination of electric fields. So you have a electric field and the magnetic field to and I don't know if you're familiar with this, but so you have the force is equal to mass times acceleration. That can be written as the acceleration is the time derivative of the velocity. So that's in an electromagnetic field, it's equal to the charge times the electric field and a cross product between the velocity and the magnetic field. And so this means that, I don't know if you remember in school, you probably, that if you have a magnetic field and you have a velocity in one direction, the force is perpendicular to that. So that's what the cross product is. Then what we can rewrite this so that we break out mass divided by charge here. And all these other entities here, the derivative, the velocity, electric field, and velocity and the magnetic field, they are all independent of mass to charge. And this is the reason why what we're measuring is mass to charge always. Because whatever combination of electric magnetic fields here this is described by this equation, and then that's why the only thing we can measure is mass divided by charge. So the time of flight is probably the most straightforward one. There all we do is we have and I should probably say that the most initially, at least, it was mostly used with the matrix-assisted laser absorption because it was an easy fit, but then nowadays it's also used a lot with Electrospray ion source. So what you have is that some way you create your ions so that they're in the gas phase, and you have them at high voltage, and then you have a grid at the entrance of the mass analyzer, and so they will all get the same, get the same. Here they have the same potential energy, and then they will get the same kinetic energy when they go through the grid. And then what we measure is just the time it takes to fly down a tube that is where there are no electric or magnetic fields. So then, so what happens then is that since they all get the same kinetic energy, the heavy ones fly slower and the light ones fly very fast. And then you record a spectrum in the detector, and then you can, usually by having some internal calibrants, you can convert the time to mass to charge. So what we have is that then charge times the potential is equal to the kinetic energy. So m times the velocity squared divided by 2. And then we have the time of flight is, we have the length of our tube is the velocity times time. And here then we can see how the mass to charge is related then to the flight time down this tube. So now, as you see, so what happens here often, the particles don't have always the same initial velocity. So that's why we get that they will not arrive at exactly the same time. So one way to improve that situation is to turn them around in what's called an ion mirror. So it's just also a linear electric field here. So what happens if two particles, two peptides have the same mass, but slightly different velocities? Then what will happen? So the one that has a little bit higher velocity will penetrate a little bit further into the mirror than the heavy one. So if one sets up the things the right way, one will be able to focus the particles, and one get much thinner peaks, and therefore better determination of the time of flight. So this is probably the mass spectrometer that's easiest to understand the details of. Another one that's also quite easy is the magnetic sector. It's not used anymore so much because it's very expensive and it doesn't give such a good. And the main thing is here, what we have is we bend the beam in a magnetic field. And what will happen is that the light ions bend more than the heavy ones. And so here we have the magnetic field, and which we then calculate how much it will bend different ions. That will depend on mass times the velocity squared divided by the radius. That's the force. So we can then calculate the radius, which depends on the mass divided by the charge, and then also the size of the magnetic field and the size of the initial acceleration field. So this one is probably was used quite a lot for analytical work, but it's also can be used for production to purify elements. And it was used during the Manhattan Project for purifying uranium-238. So in Oak Ridge, they had very large, many setups like this to just separate uranium-238 from uranium-235. So then we have something called a quadrupole mass filter, and here we have the ions go through a quadrupole field. And the way that works is that we have both a direct current field and an alternating current field. So what happens is that depending on at any time it will let through a small window of mass to charge ratios, which are the ones that are resonant. So they will go through and go to the detector, while all the other mass to charge ratios will either collide with the quadrupole rods or with the not make it into the detector. So usually what one does is that one scans then this what is the resonant mass, so that one gets a mass spectrum from this. And then one can, the quadrupole ion trap then, on the other hand, here we can capture the ions and have them go around inside the quadrupole. Also by a combination of direct current and alternating currents. So then the probably right now the biggest and most the mass spectrometers that give the highest resolution, so the thinnest peaks, is the Fourier transform ion cyclone resonance mass spectrometers, and they're big. So this is just shows an example of one in Holland, so there's a big magnet here, and it's quite complicated to operate this because you have to cool the magnet and you have to and most of them are done for very specialized research, I would say. And so here again we have the same as we had for the magnetic sector, that we bend the peptides, but now we make them go around many times. And the better, and then here is when we use the detector that doesn't destroy them but looks at the mirror current. There, but again we get that we measure the mass to charge that depends on the magnetic field and on the frequency. And here of course we need very good vacuum. In most of these we need good vacuum, but here we need even better vacuum because we need the ions to go around many times without colliding. And this is, oh yeah, so this is Beatrix Uberheide who runs the core here. And the probably nowadays most popular mass spectrometer is called an Orbitrap. And most people want to use this. And the nice thing with this is that here you don't need a magnetic field, so you can use an electric field but get the same idea that your ions will go rotate many times, and you look at the frequency in the axial direction as they move in the Orbitrap. But not having have a magnet is much easier it makes it much easier to operate. So if we look at one then how a quadrupole time of flight mass spectrometer is used. So what we have is that we have an ion source. Oh yeah, so now we're going to look at some hybrids where people put together different. So the ion source, then we have first a quadrupole, and then we have a fragmentation chamber. This is usually also another quadrupole, but in that case, the quadrupole is just used to uh, while the collisions happen, to focus the beam, and so that it doesn't become very big. And then we can have a time of flight as a second mass analyzer. And or we can have three quadrupoles, so that one is the first, the fragmentation chamber is also quadrupole, and then yeah, so that's, and then we're going to look at a little bit how this one works, because this is a classical one that can be run. So the different modes are that you can open up mass analyzer 1 and let everything through and not fragment in the fragmentation chamber, and just use scan mass analyzer 2 to get survey spectra. So this now you get the survey of what's there. So the next thing is that you then, after you know what's there, what you can do is then select one of these M over Z's and just let those ions through, and then fragment them in the fragmentation chamber, and then scan mass analyzer 2, so that again, and get fragment mass spectra. And you can switch between these two modes quickly. Then you can do other little bit fancier things. For example, you can fragment and scan both mass analyzer 1 and 2. And you can set up so that there is a constant difference between the mass that you let through here and that you let through here. So what we're looking for in this case is now a loss of a specific mass. So for example, people are often interested in phosphorylation. So you can set it up so that the difference in, let's say you're looking for doubly charged phospho ions that are doubly charged and are phosphorylated. So you can then set this up to so that you know that the charge is 2, and so when the phosphorylation is lost, you also lose water, so you lose 98. So you set it up to the M over Z difference to 49. And then you get a survey, and you find out which peptides are phosphorylated. So now we have so this is, together with the orbit trap, usually has a linear ion trap in front. And then you can use it in many different modes. So if we start with the first mode, that we can just use the linear ion trap to both measure, just measure the mass of peptides, and we can then fragment them and measure their fragments. So that's just on its own. But then we can also just use the orbit trap to measure mass much more accurately. So roughly in the linear ion trap, where most people run it, maybe the accuracy is 0.4 Dalton. So it's not very accurate, but on the orbit trap you can get down quite easily down to 10 parts per million, which is much better. But it takes a little bit longer so you have to decide if you want to measure a lot of things very fast but not so accurately, or fewer things more accurately. Then one can use the linear ion trap to select out peptides, send them to another fragmentation chamber, which is called higher collision energy dissociation, and then measure them in the orbit trap. And you can do a lot of combinations of this. And this is, I'm just going through this because people have thought a lot about how to combine these and how to best do these measurements. And this is more schematic, a little bit closer to reality, how this looks. So what we see, so here we have the electrospray source, and in this case, as you see, the needle is at an angle. And has been a lot of debate. So the idea is that all the neutral molecules will go off here and not straight in and make the mass spectrometer dirty. But it varies how people do this also. Then you have all sorts of lenses to focus the beam and to transport it. And then here we have the linear ion trap. And in this case, actually, it's two linear ion traps. One has a higher pressure and one has a lower pressure, and this makes it more efficient. And the high pressure is better for fragmentation, but the low pressure is better for the measurements. Then again, you have other transportation devices. This is the HCD cell for collisions, and then down here is the orbit trap. So then,
I have a real world question about this. Is that suppose if you have something that you want to do a mass spec about, and then you go to a core in order to get the mass spec done, is it worthwhile for the person to know upfront what sort of a setup is there in the core because of all these differences?
no, of course, yeah. I mean, most modern cores nowadays probably would have an instrument like this. Not all of them, but a lot of them have it. So definitely the
choice of the instrument is something that even the end user, without knowing anything about mass spec, should at least know about.
yeah, I mean, it's a good idea always. Yeah. So then you can collect data in several different ways. And I'm just going to go through two sort of general ways. One is called data independent, where you usually you decide in advance that you're interested in a few proteins and you're going to look for a few peptides from each protein. So independent of the survey scan, and you might even decide not to take a survey scan. So the MS is what we denote the survey scan, and then the fragment scans we write as MSMS in this case. So that so here you just measure the mass of what's there, and when you do MSMS, and you have a fragmentation in between, you select with one mass spectrometer fragment and then measure with the other one. So in this case, what we do is we decide we're going to do a survey scan, but then independent of what we find in this survey scan, we're going to then follow that by isolate these three in these three windows and fragment. And as you see here, there's nothing we can see there, but we still fragment and measure those. And then, but what will happen then, maybe at the later time, there is maybe some signal appearing here, and it grows, and then we have another signal, and so on, and then this disappears. But we have this case where we don't see anything in the survey scan, but we have continued to fragment at this point. And what it turns out to be that in because you isolate and fragment again, so you spread out over the whole mass range, you get much higher signal to noise ratio in MSMS. So even if you don't see anything in the survey scan, you might be able to get a decent fragment spectrum in MSMS, and that's why this when you do targeted mass spectrometry, you can get much higher sensitivity. And you also get much better quantitation because you follow the peak and the fragment at many points across the peak. So what probably the most popular way to do this is to do data-dependent acquisition. And here what you do is you say that I don't know what's there, I just want to see what's there. So you take a survey scan, and then you see that you tell the mass spectrometer to quickly analyze the spectrum and find peaks, and then start fragmenting them. For example, starting with the most intense here. So you would take mass spectra and fragmenting them one by one. And let's say, depending on which instrument you use, maybe you, for each survey scan, you do 10 fragment mass spectra. Or sometimes today with the fastest, and I think you can do 20 even. And then what you do is you, for the next round, when you take a survey scan, you exclude the ones that you've already done, so that you get a chance to fragment some of the smaller peaks. And this is called dynamic exclusion. So you do this, and this makes you able to get a better dynamic range when you do this. So then, so for all of these things we need the vacuum system. So there are different kinds of vacuum pump, but they're all basically pumping out differentially, and so that you have a reasonably good vacuum. So as we saw in the MOLDI system, we have the atmosphere completely outside, but usually in most electrospray systems, the ion source is outside in the atmosphere, and we have to bring the ions into the vacuum system. And so this shows the most common vacuum pump, which is, as you see, it's a bunch of blades here, and this rotates at very high frequency. So then we should start looking at data a little bit. So as we said before, we have mass to charge on the x-axis and intensity on the y-axis in the simplest case. But then we have a bunch of other dimensions also. So we have the time when we do chromatography. We have, as we said, the peptide M over Z and intensity, but then we also have the fragment M over Z and intensity, and so on. And in principle, we could continue. It's not done that often, but sometimes you do two fragmentations. So you isolate the peptide, fragment it, isolate a fragment, and fragment the fragment, and collect the spectrum of that. There are experiments where that's done. So there are many dimensions, and so this is now matrix-assisted laser desorption data collected in a time of flight. So here the structure is rather simple. So we have peptide intensity versus mass to charge. And if we look in one region, we see that we have many peaks, but we can nicely see the isotope envelopes of the peptides. So yeah, that's the other thing, that peptides, they don't just show up as one peak, because we have heavier isotopes naturally abundant. So they show up usually as a group of peaks. And so here what we see is that we have at least 3 very strong peaks. Then we have a few more that are smaller. But you see that in the matrix, it's typically we see a peak at every mass. There is a peak. So that will come back next lecture. We're going to talk about how to detect signals, detect peaks, and we're going to have regular electronic noise, but we also have this chemical noise, that we have a peptide or some molecule that's at every mass. So if we look at this a little bit closer, we see that the actual noise is quite small for these peaks. We see a little bit of noise here, but we have then this more chemical noise that it's at every mass. So even if you look at the region that's really, the peaks look very small, we see that we have quite good peptides. We can distinguish the peptides, but again here we see that how we have a very serious case of chemical noise because these peaks are smaller. And we see that then what we have the sort of electronic or statistical noise is much smaller in this case. So now if we do look at electrospray, liquid chromatography, mass spectrometry, here we can, for example, show the mass spectra as a function of time and m over z. So here each of these blob is a peptide. And what happens is that these peptides, at some time they appear and then they disappear. And here we see the higher isotopes. And as you see, sometimes there is a little bit of a tail, so they don't disappear. And sometimes this tail is very long. So that's something that one should avoid, of course, because ideally they should appear and then just disappear pretty fast. But not fast enough so that one should be able to have time to fragment the peptide. And these X's here shows where the MS spectrum has been collected. And that's the other dimension. So for example, for this, we fragmented it and we got a very nice fragment mass spectrum. So then a little bit about charge. And so we need charge, otherwise we don't see the molecules. So the two techniques put on different amounts of charge. So for most, when we look at peptides, we usually have singly charged peptides when we do matrix laser desorption. But for electrospray, it's usually more like 2 or 3 plus. Depending on, of course, the size and what kind of amino acids we have. But typically this would be the difference for peptides between electrospray and MALDI when it comes to charge states. And that, so what we then, to calculate mass to charge, so what happens when we have positively charged peptides, we have the mass of the peptides, and the charge comes from protons that are attached to the peptides. So what we take the mass of the peptide and n number of protons, and then we divide it by that same number to get, and that's why we have the 1 plus at the highest mass to charge and 2 plus and 3 and so on going down, because we divide. And then for proteins, again, we have this difference that we have many more charges in electrospray than in MALDI. But even when we go from, when the peptide's size increases and we get up to more proteins, then we get more charges because there's more room to put charges also, and more basic residues. So just a simple calculation would be that, let's say we have a peptide mass of 898. So the 1 plus will be 899. So we add 1 and divide by 1. And then 2 plus will be 450 because we add 2 and divide by 2, and so on. So it's quite straightforward how to calculate the masses, but one should remember this formula. And of course, these are just integer numbers, but when we nowadays, if we measure things down to a few parts per million, we need to use the exact masses of the proton. And in some cases, if we really measure mass, well, it's if one, instead of using the proton mass, uses the hydrogen mass, it's not good. It's not good enough. So one has to use the exact numbers. And I'll give you a list of those numbers so you can have them. The other thing that I mentioned was the isotope distribution. So a peptide is represented by several peaks. And so when we have lower masses, it's the first, what's called the monoisotopic mass that's dominating. But when we go up in mass, the higher peaks start dominating. So the monoisotopic mass is when we have only carbon 12, only nitrogen 14, oxygen 16, hydrogen, and sulfur 32. So that's the lowest mass. But then naturally we have a small percentage of higher isotopes. And the one that gives the biggest effect is carbon 13, which is about 1% naturally occurring. And that's why when we go higher up in mass, the chance that at random we have at least one higher isotope increases. And now, sorry about the formula, that doesn't look like it should. So if we only look at carbon 12 and carbon 13, we have the 1% probability that it's carbon 13. And if we have n number of carbons, then we can, and m is the number of carbon 13s, then we can calculate the relative intensity using a binomial distribution. So that's, I'll fix this formula. So what happens is that you can approximately, if you only consider carbon 12 and carbon 13, calculate these relative intensities. And of course you can then, by extending this to all the higher isotopes, also do that calculation. It's pretty straightforward. So if we do that, we can get the intensity ratio between the the second isotope and the first one. So this is just the ratio between these, and that increases linearly with mass as expected from binomial distribution, and the ratio between the third peak and the first peak is quadratic. But the consequence of this is that if we have a protein, and we can, even if we can measure it very well and get all the isotope distribution, separate all the isotopes, what happens is that the monoisotopic mass is done here, and it's very small, even for the GFP, which is not a very big protein. So we have to then figure out from this distribution exactly where we would have the monoisotopic mass, which is not always so easy. So the other thing we need to worry about is resolution. So so what most people refers to resolution is really resolving power. So at a certain mass, what is the width of the peak at that mass? So for example, in this case, if we have a M over Z at 500 and the width is 0.5, then we have our resolution or resolving power is 1000. So this is something you'll hear, and that when people talk about their mass spectrometers. So then here is an example of where we have ideally we have very thin peaks. This is the isotope distribution, but then we can have, if we have a less resolution, the peaks widen, and sometimes they widen so that we can't really resolve the different isotopes, but here we just have a little shoulder for the second and the third peak. And this is a higher mass where we again see that we get these shoulders, but the peaks can be. So ideally we want to be here, but that's not always possible. Yeah, so this is another example when it comes to resolution. So what resolution do we need to differentiate a 1600 Dalton peptide that carries either an acetylation or a trimethylation? So this is the masses are very similar, as you see, and then what we can calculate, we take the difference between these two masses, and we take the mass of the peptide and the difference and divide it, and then we get what resolution we need at that mass to distinguish them. So then, as we said, we're always measuring mass to charge, but because we have these isotope clusters, we can determine what the charge is, and then we can calculate what the mass is. So if we have 1 plus charge, the difference is 1 Dalton, or 1 m/z unit here. If it's 2 plus, it's 0.5, and 3 plus, 0.33. So then, of course, depending on the resolution, if we have high resolution, we can always determine the charge, and then at some point, if the resolution goes down, we won't be able to determine the charge. So this is an exercise for you. So what is the charge in these two cases? Yes. Why?
Because the difference between them in the first case is 0.5.
0.5.
0.5.
Yeah.
And in the second case, 0.2.
Yeah. Yeah. Exactly. So that's the. So then since we have this, now you starting to get an idea of the structure of the mass spec data. So one of my colleagues, Manor Ashkenazi, developed a system so that one could be able to look and explore this data over the internet without having to. So classically, you have to install all sorts of software to look at these mass spec data, but he developed a system so you can look at it on the internet. And his inspiration was that in astronomy, the data has many different dimensions, and they are usually making it available so that you can slice through this data in different ways to allow you to look at the data without downloading it or installing lots of software. So he developed a system for to do this with mass spec data. So this is now an example of that, of a mass spectrum. So now, first we're looking at one peptide that's at m/z 737.7, and this is the 3 plus of this peptide here. And now we see, so this is time on the x-axis. So we see the peptide appears at some point, and then it intensity increases, and then it disappears. And I don't know if you see these small black points. There's one there and one there. These are where we have fragmented this peptide. So if we look closer at this fragmentation here, we see that we get a nice fragment mass spectrum with B and Y ions. In this case, the B ions are more intense, and it corresponds well to the peptide that we expect. And then if we continue and look at this in more detail, we can get which masses we can observe, and here we can also look at in more detail what the other ion types or losses of neutral losses of water or NH3 and so on. So this is sort of an interface where one can go into more detail. Then we can also go to the previous survey scan to look at what peptides came out of the chromatography at the same time as our peptide here. And we see that there are a lot of peptides. And this is a very typical case that we have a complex mixture, and at any time we have lots of different peptides. So these are all different peptides in different charge states, and our peptide is this purple one here. Not at all the one that's dominated here, but because we isolate it, we are able to get a good fragment mass spectrum of it. So then we can continue and look at zoom in a little bit here. So we're going to zoom into an area around our peak here. So we see this is our peak, and then we see there's several others, but let's say we want to look at this one here. So now we can see that this is our mass spec. Now we're looking at the time profile again. So this was our original peak. And then this other peak that came out at the same time is slightly shifted in time. So it doesn't go through the chromatography exactly the same way, but the two peaks overlap. So what I'd like you to do is to go to this website and have a look at some data. And there should be some instructions. So first, this interface. So what we can do is I can bring this up, but let's take a few questions before, if you have any now. Otherwise, then we can explore the data a little bit. Yeah.
So, could, in theory, one then introduce artifacts into the final data, into the final result by not having like a noise threshold?
Yes. So it usually, yeah. So that problem comes in several different ways. One is when you try to do quantitation, and you get at the same time peptides that don't have different sequences, but they come at overlap in the chromatography and have very similar mass or identical mass in a lot of cases. That's not at all unusual. So then you have two different peaks that overlap, and you think you're quantifying one thing, but it's really yeah. And even if you do, so this is when you do in the full scan, you can do, this happens, but also when you do MSMS, even though you isolate and fragment, you get a lot of interference. So this is a big problem, yes. And that's, there have been different attempts at how to overcome that. And we're going to talk about these things later on quite a bit.